So we're presenting a very large amount of plankton data, and I hope I've listed all the individuals and institutes and funding agencies. Apologies if I've missed anybody out. So the structure of this talk, I'm going to start off by describing the plankton observations from last year at the L4 site that Tim has given a good introduction to. Then I'll hand straight over to Jeanette, who's going to be presenting the picture from last year on the gelatinous zooplankton. But the main part of the talk is actually putting a sort of wider scale context on it, looking at the trends from last year in relation to the long-term climate-induced changes in the plankton, and that is from the whole of the UK. And the last bit of the talk is looking at the implications of the changes in the plankton for the rest of the food web. So starting off with the L4 observations and the phytoplankton, we haven't fully analysed the data and got it into a quantitative way, but this is just some of the highlights and snippets from the last year. This slide is for the phytoplankton, starting with the bottom left. As Tim described, the spring bloom was well underway in April. It was a mixed bloom of diatoms and phascistus. This is one of Claire's pictures of the diatoms, but I think there was diver observations from around the West Country on the phascistus as well. And that transited into the summer, as Tim described, a very warm, settled spell in the summer, and we got quite a big coccolithic bloom at L4. If you remember, I think it was 2020, we also had some really nice settled weather. That was the first lockdown year, also really big coccolithical blooms. So this is a little bit reminiscent of that, only on a smaller scale. Coming through to autumn, top right, an unusual bloom of silicoflagellates, and later on in the year there was a return of some of the warmer water species and a couple of new records. Illustrated here, just one of the diatom species, which was a first for L4. So that's the phytoplankton, a couple of the zooplankton observations. We do weekly measurements of the egg production of Calamus at L4. They've been going for 30 years, which is providing a really good index of the food quality. And there's, in the summer, sort of May to July time, there was a pronounced dip compared to the long-term average. And this declining food quality in summer is a theme I'm going to return to in a little bit. Also in the summer, there was an unusual occurrence of the salps, and that's fairly new for L4, and I think a much more widespread occurrence. But with that, that's a good cue to hand it straight over to Jeanette for the gelatinous.
So, thank you, Angus. So, I'll just put this slide up here to show people who may not be sure what we mean by the gelatinous zooplankton. It covers a wide range of organisms, from the tube jellyfish, the scapozoa, they're closely related hydrozoan organisms that come in a wide variety of shapes and sizes. And then we've got two groups that are completely unrelated to the stinging jellyfish, but the cone jellies and, as you say, the salps. They come in a huge range of sizes and shapes, but we tend to group them together because they live predominantly in the zooplankton and feed on the zooplankton as well. So what were the top sightings in 2022? So these sightings are a collation of our sort of visits to the beach, but also things provided by PML, by this particular meeting, but predominantly they've come from posts to social media, which means most of them are based on things that you can actually see with the naked eye, so we're not going to be able to tell you much about smaller life stages. So we had lots of the moon, compass and blue jellyfish. Amongst the hydrozoans, the top sightings were crystal jellyfish, the Portuguese mudwort, vitamin sailor, and we also had lots of cone jellies. And we've had these reported for the last 2 years, and what's interesting is we're having these reported as swimming observations, so they're live animals, whereas previous years they've been reported mainly as strandings. But we had some rarities as well. So we've been collecting this data since 2019, and the mauve or purple stinger has only been reported once, and that was off the Minick Theatre in September last year. The barrel jellyfish, previous years it has been sighted more, but there was only one sighting in February last year off the Eddystone. You can see some of the hydrozoans which come in, as I said, all kinds of shapes and sizes. One of note is probably one in the middle, which has been provided by PML from L4, and I'm informed that this is something you'd associate with incursions of warmer water into the area. And then at the bottom we've got some pictures of the salps, so one picture on the right you've already seen, but at the same time these were taken inshore off the coast of Cornwall, and both life stages were seen together. I'll really quickly show you the seasonal patterns, because I know we have to move on. You can clearly see there that the barrel jellyfish has not been seen in great numbers inshore since 2019 really. The compass and the blue and the moon are doing quite well and seem quite well established along the south coast of Cornwall and Devon. And then amongst all the others, we've got the crystal jellyfish, which had previously been considered to be a rare species. And these sightings are probably a grouping of 3 different species, but they seem to be doing quite well along the south coast of Cornwall and Devon. The Portuguese man-of-war and by-the-wind sailor we usually find as strandings on the coast after stormy weather. It's kind of noticeable that in the summer this year, or last year, 2022, they were seen again as strandings around the coast. The oddities that I mentioned in the hydrozoa, you can see that they're just really things that have been noticed in 2022, so we don't know whether they're going to occur again. And the cone jellies, as I said, seem to be doing quite well the last couple of years, and were previously not reported in such high numbers. And I hand back to Angus.
Thanks, Jeanette. So that's what we're describing for the plankton observations from last year. Now I'm going to put a wider scale context, looking at these trends in relation to the long-term changes at this L4 site. So this just gives an introduction, setting the scene for rising temperature and declining summer nutrients, particularly nitrate, and that's quite important. These are 2 of the major stresses on the zooplankton and the phytoplankton. So these plots, the red is the time trend of the summer months, it's typically stratified, and the black is the rest of the year. So looking at the effects on the phytoplankton, the bottom left is a bulk index of the phytoplankton, the chlorophyll A, and that's roughly overall declined by about 50% over the last 30 years. That's a really important fact that I'm going to come back to later on in the presentation. That decline in chlorophyll A is reflected in declines in some of the major functional groups, but mainly in the summer period. And those summer declines were also happening in some of the major zooplankton, in particular both large and small copepods, but also other crustacean zooplankton and fish larvae for the summer. Not all of the taxa were declining. There's a counteracted increase, and this is a year-round increase, in the mirror plankton in particular. They're the pelagic larvae of benthic invertebrates, but also some of the other non-crustacean zooplankton, and particularly some of the gelatinous species, the filter feeders and the carnivorous taxa that Jeanette has mentioned. So they tended to be year-round increases. So we're seeing a little bit of a change. The classic food web, if you can imagine, from sort of like diatoms to copepods to fish, is slowly declining in importance, particularly in the summer months. So that's the L4 picture. We've also got a network of time series stations which were developing as part of policy reporting. This is Matt Holland's slide from the OSPAR QSR 2023 assessment. So we've got really good coverage over the last 60 years from the continuous plankton recorder. That's the left-hand plot. That's complemented very nicely with very high resolution time series from much more coastal locations around Europe. So this is giving us a really nice spatial and temporal picture of trends in the plankton. So this is one of the key figures from this QSR 2023 report from Matt Holland. There's quite a lot going on here. It's just basically a heat map of change. So the bright oranges are the increases in the taxa over typically the last 60 years. The deep purples are the declines. So a couple of key things going on here. Noteworthy is the meroplankton, just as at L4. There's a very, very widespread and large increase, roughly a doubling of the meroplankton right round this area, right around the UK. There's also something weird going on in the North Sea, which we can't really get to the bottom of, because the plankton trends seem a little bit more stable and, if anything, increasing in the North Sea, which is a bit puzzling because it's warmed much quicker than the rest of this area, and it's suffered increased fishing compared to the rest of the area. So we don't really know what's going on. But in the west of the area, particularly west of the UK into the northeast Atlantic, there's big declines in copepods, diatoms, dinoflagellates. So these are year-round declines, so they're similar to what we're seeing at L4. So that's the wider scale context. Now I'm going to move over to looking at the implications for the higher trophic levels. How are these changes over the last 30 years that we're seeing related to some of the higher trophic levels? So just to recap, as I've said, we're seeing a gradual replacement of this sort of classic food chain from phytoplankton blooms, copepods, fish larvae, and that seems to be particularly in the west of the UK and in the summer months as well, in this nutrient stratified period, nutrient limited period in stratification. So we seem to be transitioning in those situations to a slightly more complicated and alternative food web. There's a dominance of smaller cells, they're relatively more important in this lower chlorophyll regime, longer food chains, which is tending to mean less efficient energy transfer up to fish, and some of the grazers are changing. So we've got an increase in abundance of meroplankton and some of these gelatinous filter feeders I've illustrated here with the salps and appendicularians, which can directly tap into picoplankton, tiny little primary producers. So that's all well and good. That's a sort of conceptual idea, but what we really want to get to the bottom of is I've given the sort of a schematic of relative sizes of fish larvae to suggest there's less efficient energy flow through to fish, but we want to put a little bit of sort of like a few more numbers on that. So we've gone for a size-based approach to look at energy transfer efficiency. So this slide illustrates this sort of size-based so-called biomass spectrum approach. This is a recent, really nice publication in Scientific Advances where they've done a global compilation of all pelagic biomass on the top 200 metres from bacteria on the left through to whales on the right. They've organised into logarithmic size bins of equal size, mass bins, and it's the total biomass on the planet on the right. And the thing about this is clearly it's a remarkably linear slope. I thought at first when I saw that it was a model or a sort of illustrative plot. This is actual real data showing a remarkable straightness of this relationship. This relationship is signifying a loss of matter as you go through the food web due to inefficiencies of energy flow in the consumption process through the food chain. And different environments have also this remarkably linear slope. Okay, just should be able to squeeze it in, hopefully. I'll speed up. Different environments have different slopes, and that is an indicator of different efficiencies of energy transfer in specific systems. So we wanted to use that linear property. We can measure the plankton spectrum on the left to estimate the bit that's harder to measure on the right, the biomass of exploitable fish, the supportable biomass of fish in these different ecosystems. So that's what we did. We compiled high-quality size spectra from around the world and related them to the nutrient status and the temperature of the system. And this is what we got. There's basically no relationship between these size spectra slopes as a simple diagnostic of the efficiency, no relationship between these slopes and the temperature, which was really surprising because models suggest there is an effect. Instead, it was related very strongly to the nutrient status, proxied by the chlorophyll A concentration. So the steep slopes, the less efficient systems are in the bottom left, for example, the oligotrophic mid-ocean gyres, and Plymouth L4 for reference is roughly in the middle. So if you remember, there was a 50% decline in chlorophyll over the last 30 years at L4. So I've plotted that as an illustrator on this plot. So it leads to a steepening of the size spectrum slope and a decreasing efficiency of the system. So you can translate that slope value, the red line, to an efficiency calculator because there's this linear property of the size spectra. So this is the efficiency of transfer up to fish. So as the chlorophyll declines, not only is the chlorophyll declining, but the efficiency is declining. That's a double effect leading to this so-called trophic amplification. So halving of the chlorophyll A leads to a 73% drop in the biomass of fish that is supportable from the system. So very briefly, looking at the implications of that, this is the output of an ensemble of Earth system models which are suggesting a decline in phytoplankton in the mid-latitudes. That's exactly why we think it's declining at L4 due to increased temperature and nutrient stress. But that translates to a much more amplified decline in the supportable biomass of fish, the so-called trophic amplification. So that's all I'm going to say about size spectra. I could go on for ages, but another really good example of linking plankton changes to higher trophic levels is actually sampling them concurrently in space and time, and that's through the CFAS Peltic surveys, which I'll describe. The logo is a really nice example of how they've integrated right through the pelagic food web. So these are slides I borrowed from Jeroen van der Kooi from CFAS, so if you've got any questions about them, please contact Jeroen. But basically the October 2022 Peltic survey was abbreviated, but it had underway sampling and CTD stations, and the main emphasis of these surveys was acoustic fish stock assessment, but they did a wide variety of both plankton and higher predator observations. So this is some of the higher predator observations. The important thing is that they're in the same space and time as some of the underway plankton observations. I'm nearly there. I think this is my last slide, in fact. So this is just an illustration of the acoustic biomass of sprats with the October 2022 survey, and I've put the L4 station in to show that there's developing technology called the Plankton Imager, which is used both on Peltic and will be deployed at the L4 buoy, and that will enable a much easier sizing of plankton, so we can develop some of these size spectrum approaches alongside traditional taxonomy to look at the changes. So I'll leave you with the conclusions. Long-term trends in plankton, not exceptional, was 22 not exceptional, part of a long-term trend, and size spectra in this underway sampling can link the plankton much, much better to higher trophic levels. That's me. Thank you.